for, I don't know, maybe our 10th seminar of the series already or something. So our speaker today is Peter Onyisi, who joins us today from the, well, relatively local today, from UT, not had to fly across the country to arrive here. And he'll be talking about the latest Top-Higgs coupling measurements from Atlas.
Thank you very much. So, yes, it was actually a very pleasant drive over this morning, so got a little bit rained on. Okay, so let's jump straight into it. So there's a Higgs boson, you've heard about it. Is it actually the standard model Higgs boson? Well, we sort of hope it's not. There are no radical departures from the expectations as far as we can tell, but the errors are still pretty large, and you're really talking about model-dependent constraints of order 15%. There's lots of space for departures from the standard model expectations to be hiding out in there. So the question is, are these things coupling to standard model particles as they should? Is it coupling to anything else? I'll come back to this plot in a little bit, but this is an Atlas combination, assuming standard model-only couplings, no anomalous Higgs-gluon couplings, for example, no invisible decays. Here's a nice CMS result showing evidence for fermionic decay, so the thing actually does generate possibly masses for fermions, which was not so clear until we actually observed the Higgs decays to dB and tau tau. And here's an Atlas result on the invisible branching fraction, now showing this is not actually so well constrained, so combined over a lot of channels, and still only giving you limits of about 30–40% on the branching fraction to invisible particles. So just as a reminder, the Higgs really serves two distinct roles. These things are not necessarily connected. The first is to solve the problem of giving masses to the W and Z. These are particles that should be massless by gauge invariance, weak charge conservation. And the other role it plays is giving masses to the fermions, which should also be massless because of gauge invariance, but for a somewhat different reason. And in fact, this whole structure of giving masses to the gauge bosons is very extremely well constrained. It has to behave in very specific ways in order to actually be mathematically self-consistent. It's not really necessary that, apart from the empirical fact that the leptons and quarks have mass, it's not really a given that it's the same particle, the same field that is interacting with those to give them mass. In fact, you can perfectly well have a mechanism that gives masses to the gauge bosons that doesn't give masses to the fermions. The reverse is not true. If you do give masses to the fermions, you do give masses to the gauge bosons as well, but there is a separation of these. So examples, a standard example would be a model with two Higgs doublets where they just have different couplings independently. The two doublets have different couplings to fermions, and what you could have a pattern where only one of them is coupling to fermions. More exotic would be something like Technicolor, which is a really elegant explanation of how to give masses to the gauge bosons, but really has stumbles explaining fermion masses in ways that are compatible with data that we have. So the moral is we really want to separately establish not just the bosonic couplings, but the fermionic couplings, and the fermionic couplings are much less well known. Okay, so the standard model Higgs coupling to fermion mass, the decay rate is proportional to mass squared. You really only have access to decays to the heaviest fermion, well, couplings to the heaviest fermions. So when I talk about the top quark, it's not decaying to tops, but it's being produced in association with them. You could say go into a two Higgs doublet model, which could change the ratio of the lepton and quark, lepton to quark couplings compared to the standard model, the up and down separately, or the overall fermion rate. So assuming generation independence, you want to constrain the leptonic couplings, and look separately the couplings to down and up type fermions. So to do up type fermions, what you really need is the top quark. At some point, we will have access, hopefully, to CHARM, but that's a high luminosity LHC project. That's not something that we can get at right now. So there are a couple of ways you could possibly get to the top coupling. I'll show them in a bit. But first, okay, so this is from a paper last year showing parameter scans over the phenomenological MSSM. These are essentially models in a parameter space that survive known experimental constraints, where they looked at, okay, so what's the relationship between the mass of the light stop and the expected modification to the TTH rate. And if you can't see this axis terribly well, this goes from 0 to 6. So you're actually dealing with models that have modifications of the TTH production rate of very large, order 100% or larger. Where even in fact some where effectively you see nothing at all. So it's not just, at this point, not just, oh, there could be very, very minor changes. In fact, there are surviving models that predict order 100% deviations. So how do you go ahead and measure the top coupling? So the highest rate way, we actually do have constraints on this now, model-dependent ones. The easiest way to do it is, in fact, the mode in which the Higgs was discovered is to look for it in gluon-gluon fusion, because that proceeds vastly, primarily through a top quark. So the problem there, and this is well measured, the problem here is that you have no way of distinguishing this top loop from anything else that might be. There could be a special higher dimension vertex that is sitting here. Whatever new physics could be sitting here mimicking this. You have no idea. So this gives you a very nice constraint, but this really assumes that you set a whole bunch of possible new physics terms to 0. If you want to really directly access this thing, now we actually want to unroll the loop in a sense, break out the top quarks. So now actually see the top quarks being produced and have the Higgs boson coupled to one of them. So actually, we like to show this diagram. I'm not entirely sure why, because most of the cross-section actually is an FSR component, but anyway, this is, I guess, symmetric, so it looks nice. So this, I like to refer to this, echoing B-factory language as we're comparing the loop measurement to the tree measurement of the top couple. So just to come back to this point about the constraints on new physics here, so if you assume standard model particles only, you actually get to these are likelihood contours, and the green's effectively 1 sigma. So if you look at the constraints on modification of the top quark coupling, so this is essentially the scaling of the standard model coupling, you actually have reasonably tight constraints, but this is assuming no new physics in that gluon. If you relax that assumption, you say, well, okay, maybe there's some new physics there. We'll just allow for direct, for some coupling to the Higgs to gluons that comes from something new. This is now the resulting constraint on the top quark Yukawa coupling. As you see, there's basically effectively no constraint here. There's a weak one coming from Higgs to gamma gamma, but it's clearly nowhere near as good as this. Another illustration of this comes from a paper, actually quite recently, showing an explicit degeneracy between various dimension 6 operators that could affect the gluon-gluon fusion production rate and the TT bar Higgs production rate. These turn out to be sensitive to these operators in different combinations. So the blue bands are where we have to be living given the constraint from overall gluon-gluon fusion production of P to H. So there's clearly a tight constraint on the relationship between these two, but we could be living anywhere along these directions. And so so these numbers here show the modification of the TT bar Higgs production rate as a function of as you change this equilomagnetic dipole coupling, essentially this operator, the coefficient of this operator here. So again, on this, so this is not really going this far is not really physically allowed by current constraints on the TT bar production cross section. But you see, you can still get order 20% deviations quite easily from adding these operators in ways that are consistent with what we found. So now that we actually have a Higgs mass number, we can take this cross-section plot, and now it looks actually quite boring because it's effectively almost constant lines. But so this is the rarest of the major production processes, we might say. It's sort of the last thing to be ticked off. So we're looking at this purple band down here at about 130 femtobars at 8 TeV. But it has a very, very distinct signature. So the thing that makes it, in fact, it's not that much harder to find than these associated production W and Z channels. In fact, the reason why it's not so much harder to find is that the TT bar pair gives you a really, really distinct event signature, right? If you're looking for W's and Z's, okay, you've got maybe another lepton, but this could be confused with diboson production, so on. But here, you're really dealing with very spectacular events. Again, to set the scale here for people who are unfamiliar, the largest decay branching fraction is into BB bar pairs, heaviest fermion, and we're heaviest thing below half the mass of the Higgs, basically. WW, which we are working on for this analysis actively, but do not have a result for yet, comes next. Ignoring glue, then we get to tau charm. And down here we have Dai Photon, which you might think is, okay, that thing is down a couple of orders of magnitude. But the thing that's great about that, nearly 3 orders of magnitude, the thing that's great about Dai Photon is it's got great mass resolution. So compared to everything else, we're not sensitive to ZZ to 4 leptons in this channel at all. The cross section is much too low for that. But we can actually hope to see a signal in gamma gamma as well. So how are we going to look for TT bar Higgs? Well, with the generic signature, okay, there's a pair of top quarks and the Higgs boson decay. So the Dai Photon is mentioned, that's a narrow bump. We can just go look for that narrow bump. BB bar is a large rate process. Now you're just looking for multiple B jets in the event. You should expect to have 2 Bs coming from the top pair decays and then a couple of Bs coming from the Higgs. You can play games to try and kinematically reconstruct, okay, that these 2 Bs should have about the Higgs mass and so on. WW and tau produce multi-lepton events, and again, unfortunately, I cannot show you these because we don't have the thing out yet, but this is actually a very sensitive way to look at them as well, because unlike BB, where you can produce bottom quarks through QCD processes, it's much, much harder to add additional leptons to an event. You have to go through some electroweak process, so you have, even though somewhat smaller rates, you have a significant reduction in not only the amount of background, but the kind of background you're dealing with. You can hope to, you don't have to go to very high order QCD to do that. And then, as I mentioned in passing, ZZ to 4 leptons, just much, much too low a rate to be sensitive at this point. You're doing top pairs, really characteristic signatures of leptons, hadronic jets, tagged jets. Here's a single lepton, sort of the top bin you would make if you were just looking for top quarks off the bat for TT bar pairs. So in this case, you expect so both tops are decaying to W and B, and in this case, one of the W's is decayed leptonically, the other W is decayed to quarks, leaving you with 2 Bs, a total of 4 jets, including those 2 Bs and the lepton. Also missing energy. It turns out we don't actually use missing energy in these analyses, so it's unnecessary given everything else that's going on. And you see the unshaded region is partly described as the TT bar production, so it's absolutely dominant even with these selection criteria. I include this plot specifically to poke some of the people who were there for CDF1 and then say, oh, look, see, top quarks, very easy, not tens of thousands of them per bit. So
why not CC with jets and
okay, so that's actually a very good question. We are looking, so neutrinos are a little tricky. We are looking into doing it with LLJJ, but that was sort of a subdominant thing.
WW is leptonic, or is it?
WW winds up being, we don't really care. So we require at least one of them leptonic, but if you can accept both being leptonic or only one being leptonic. You need at least one to fill out the signature. The thing is, you need something that distinguishes it from just TT bar plus jets. So if it's JJJJ, then you don't have that. Okay, so
I guess missing ET doesn't help.
Missing ET really doesn't help. I mean, they're not super high missing ET events.
They're starting to balance out each other and
yeah, I mean,
pushes to the wrong.
So you're producing these events generally sort of right at threshold. There's no real boost to most of them. You are getting, there's not very much missing ET, and the resolution is just not really good enough to play the games you want to do to try and resolve things like, having 4 leptons, 3 leptons instead of, it says 3 neutrinos instead of 4, right?
So then how do you play against TT-bar double?
For which case? We're getting it.
Well, stop pair plus the keys.
Yeah.
So it's a W, and you say you care only about one lecton.
Oh, but we count the extra jets. So it has,
It's
so
analysis too.
right, okay, so we're talking about analysis that's not in here yet, but if you imagine, for example, WW, one top quark decays, so there's a semi-leptonic top, lepton plus jets top, one of the W's decays leptonically, you can wind up with the same sign event, so that distinguishes you from top. Okay, so finding top pairs, so for the first of this, we're only going to deal with gamma, gamma, and BB, so we can separate this. So you're getting essentially 100% of your decays via T to WB, so 68% of the W's to quarks, 11% each to E mu tau. Taus at the LHC are difficult, and unless you're really specifically targeting something where taus are enhanced, quite tricky to do, so it's rather rare that we explicitly target taus, and we're not doing that for this talk. So the top pair can be, because you either have 2 leptons, 1 lepton, or no leptons. The largest single component would be no leptons at all. You see actually sort of this sliver here, this 4% here is when very nice dileptonic component. But if you really want to get statistics, you have to try and access the lepton plus jets as well. The alpendronic is very interesting in that there's, of course, so much of it, but you have to be able to separate that from multi-jet events. And it's qualitatively very, very different analysis. Okay, so before we get to the Atlas ones, here's the CMS results. And I have to say, in my embarrassed role as the co-convener of the Atlas group, that we're way behind in getting our stuff published. So CMS, so this is sort of setting the scale of what to expect from us. So you actually see these error bars between different channels, so gamma, gamma, BB, hadronic, 2 hadronic taus. Okay, 4 leptons just has a very big error, so don't worry about that. 3 leptons and the same sign, 2 leptons, so these are WW, tau, tau sensitive mostly. That in fact, the error bars are not that far off from each other. So each channel has something going for it and something, gamma, gamma has great mass resolution, but okay, your rate is very low. BB has lots of rate, but you don't have, you've got lots of background that you need to understand, and the shapes are difficult. So here's the equivalent limit plot. So in fact, if you look at the number, the combination, it's actually at 100% of the standard model standard model measurement at this point. So it's 2.8 plus or minus 1, but okay, it's times the standard model. But we're getting to the 100%, and we can shrink those errors down. Okay,
All right,
it's
Peter,
driven.
can I
Yeah.
ask a dumb question?
Yeah.
I'm sorry, I was thinking about your all jets thing. Why not do this as a ZZ plus 6 jet analysis?
ZZ plus 6 jet.
Right, so in some sense, it's the Higgs goes to ZZ. So if what you did was a ZZ plus 6 jets, but you know darn well that your 6 jets need to be 2 Bs, the other 4 need to be 2 Ws, and the whole 2 combinations need to be TT bar, you're going to get a huge branching fraction, and you're going to be getting rid of most of your background
ZZ
anyway.
to jet or BB.
Doesn't matter.
I'm pretty sure that.
I mean, you've got so many branching fractions, you're chopping it up no matter what
Yeah.
you do. But
Yeah, well, the reason I say this is because it's actually an interesting question. I don't think we've thought about it for, if we did ZZ to BBB, then we would wind up with 6 B events, and that would actually be kind of distinctive. The problem is if you're just adding jets to a TT bar event, then
no, but again, I'm sort of thinking about it the other way. That you're saying, in some sense, the idea is you're looking for TT bar in all jets. So you get
Yeah.
a big branching fraction. Right?
yes, but what's the Higgs doing?
Going to ZZ.
ZZ to what though?
Doesn't matter.
It does matter, because if it's ZZ to leptons, there's no rate. If it's ZZ to jets, you can't distinguish it from TT bar plus jets. There are a lot of jets. The
No, but
combinatorics just wash out. You
But there are
can't
so many
actually,
you gotta get, okay.
you can't do that. If you've got that many jets, your reconstruction will pretty much always succeed in giving you a solution. Whether or not, there's just so many, if you're dealing with 10 jet events and you're asking, okay, there's got to be 2 W candidates in that, there'll be 2 W candidates.
Well, but if you've got the Bs, you've gotta have 2 Ws and 2 Zs.
Yeah, but
and the
you
top
still got,
one.
you've got
Alright,
6
I'll
jets
take
to
your word
make
for it.
W's out of it, yeah. It's hard enough as it is with, with H2BB. Okay, so 2 Atlas results here, gamma gamma BB, we are looking at the others. We would hope to have everything here by the end of the year. And then I'll briefly talk about some private extrapolation for multi-lepton. As a proxy for actually showing you actual Atlas multi-lepton results, I'll show you our multi-lepton estimates for the far future, which we did for CMS. Okay, here's Atlas. It's a detector. There are some people for scale. It's a pretty standard detector of the hermetic symmetric kind. One thing that's important, so in terms of specific object performance, I'll talk about p-tagging here. So especially for the BB analysis, right? We're asking, okay, we want to find some large number of p-tagged jets. We are finding the jets that came from B hadrons using a multivariate tagger, which combines the impact parameters of the tracks in the jet, associated with the jet, and secondary vertices that can be found there. And we're able to tune the working point of this, so the number to keep in mind in general is 70% efficiency for approximately 1% mistag rate. So in the region, this is basically where our jets live anyway. We're not really dealing with jets above a couple of 100 GeV, so this is the 100 GeV bin. And then the mistag rates essentially 1%. And the simulation actually does a reasonably good job. We're dealing with scale factors of 0.95, 0.98.
So this start rate is set to 2 meters per far? This is so far.
Yeah. So this is not strongly dependent on the run through. Okay, so Dai photons. So this channel is actually so clean by requiring 2 photons. I mean, this is not something you need an electromagnetic process or Higgs to make these. And one very nice thing about Atlas is that when you actually ask if I require 2 photons with these quality criteria, you find that almost all those events are actually photons. They're not jets faking photons. They are actually photons or electron bremsstrahlung or something. So the main challenge is not to clean up your photons. The main challenge is actually to reduce contamination from other Higgs production. Because you go and find a bump at 125 GeV, that's great, but is that actually TT bar Higgs? Is that something else, some other Higgs production leaking into it? So it's actually qualitatively a very, very different analysis. The only one where backgrounds from other Higgs modes are actually relevant. So this analysis gets split by top pair decays. It's lepton plus jets. So once you require a lepton and a p-tag, so you're targeting either lepton plus jets or dileptonic decay modes. Once you require that, that's actually strong enough to remove all the other major Higgs production modes. There really aren't other things like WH, ZH, vector boson fusion, gluon fusion, don't produce an extra lepton on a p-jet. All hadronic, now that has contamination from a lot of things, especially gluon fusion. The problem is now we're extrapolating from the leading order process, which is already a leading order process with 0 jets out to a bid with 6 or more. So the extrapolation uncertainty on that, I mean, of course you can just simulate it, and that's what the Photon shower gives you, but maybe you shouldn't trust that. So actually very tight cuts are put on this in order to suppress the gluon fusion component of that. And in fact, this this is the main difference between our sensitivity and the CMS sensitivities, where we really try and suppress the gluon fusion much more. So here's the Dai Photon Selection. I won't bother you too much with the details. We actually do use the Dai Photon triggers, and the nice thing is this essentially goes along as a free ride with the gluon fusion analysis. We just use their trigger. In fact, pretty much use their selections everywhere for the objects. So there's a little bit of a game played with different working points of the B tagger along with the number of jets in the event. So you can say for the hadronic channel, if there are 6 jets, then and we have 2 Bs, then we can allow those Bs to be loose Bs. So we take a looser working point with a higher phase rate. If we only have 5 jets, we can raise the jet threshold. We can require 2 tighter Bs, or let's say if we have 6 jets and only 1 B, that's fine, but it has to be a really good B. And in the end, you wind up, so the leptonic and hadronic, okay, they're both contributing similar numbers of events. The hadronic has a lot bigger background. You see we're successfully able to suppress the gluon-gluon fusion. Even with the tight selections, it's still sort of 0.7% gluon-gluon fusion in this bin, but at least that's relatively small.
What is NH and NB?
This is the number of Higgs candidates you expect. This is the number of background events. The background's estimated from sideband regions, so you're doing it. So you're still expecting, so that's why the uncertainties are really big, because we don't have very many events in the sidebands to make the estimates from. But even then, you still are actually expecting fairly significant backgrounds. So it's not, it's,
But Peter,
Yeah.
the first and third one
First
is
and third.
exclusive.
sorry?
The first and second type is exclusive.
The leptonic is inclusive in the number of
No,
leptons.
6 jet.
Oh, okay, yeah. So yes, it's greater than or equal to 6.
Right.
Yeah.
Third one,
Third one, yeah.
it's not inclusive, exclusive.
It's inclusive in the sense that it can be more than 1 B at 60%. We don't
So
care.
you accept any of that?
Yeah. It's an or of all three.
Okay, okay.
Yeah, or. Sorry. Okay, so yeah, we're still talking about order 1 event on the background of 3 to 4. Most of these being TT bar photon. Okay, so here's a as we say, typical leptonic candidate. There's a muon, this is a single lepton event. There are 2 photons. There's missing energy, 4 jets. That can't be right. There must be 4 jets there, which is not showing up. No, sorry. This is the leptonic category, so there can only be 4 jets. That's right. That's exactly what you expect in the leptonic category.
Math aligned with the jets.
No, there's met. Okay, fine. It's aligned with the jet, but generally that isn't an issue for us. We're not really cutting on met anyway. So this is a jet counting experiment, in fact. So if we were really worried about how large the met was, we would care. Okay, so before I show the results, one very interesting wrinkle of this channel is the fact, because the leptonic category is so inclusive that we're requiring a lepton in the jet, you're sensitive to not only TT bar plus Higgs, but also single top production plus Higgs. And it's rather unique, it is unique, in being in a channel that's actually sensitive to this. The thing that's interesting about TH is that these 2 diagrams, where you have Higgs radiated off the top and where it's radiated off W in this exchange, destructively interfere with each other. So in fact, the overall rate in the standard model for this is quite small. If you reverse the sign of the interference, it becomes very large. It becomes comparable to TT bar Higgs. So in fact, you can exclude the wrong sign of the interference here just by looking for mostly the lepton plus jets category. And saying, well, if the cross-section's too big, if we inverted it, we get a much bigger cross-section than the standard model, so our limits limit correctly the wrong sign. There's also an interesting interplay with the Higgs to gamma-gamma range, which is also set by the interference between W and top loop. So both of these effects come into play. In fact, if you reverse the sign of the interference, you also would get a factor of 2 increase in the branching fraction for gamma-gamma. So you expect overall a very big increase if you were at -1 times the standard model coupling instead of +1. So here are some data plots. So here are the categories, leptonic on the top, hadronic on the bottom, 8 TeV on the left, 7 TeV on the right. Okay, no bumps are jumping out at you from this. In fact, the fitted, okay, so the lines you see here, the bumps you see here are the results of that's the best fit, okay? It is what it is. In fact, you clearly have to be extremely conservative in your background shape, right? You're not allowed to let it vary as much as you want because it could pick up all sorts of weird shape effects. So we do use things like loose photon control regions to make sure that the functional forms we're choosing make sense.
So what is the counting experiment for these four?
Well, okay, it's not the counting experiment. The experiment is basically we actually do fit. There is a likelihood curve of. Well, we know what the mass is. We put in a mass hypothesis.
Right. I mean, so like the top left has got 5 MS.
Yeah,
I don't know
but
how to integrate that solid line, but that doesn't look like 4 not Higgs and 1 Higgs.
Right, but so when we listed numbers in that table, I was taking some cut around the mass. So you see, if you cut here, then
Yeah, I mean, okay, that's consistent with 1 plus, okay, but I meant from like 105 to 160.
yeah,
I mean,
that's normalizing the background level. So we have some exponential shape, decreasing shape. We say, okay, that's what the background shape will look like. We stick a signal on top of that, we find the best fit value of the signal strength.
So how many events you expected here?
It was about 1 total, 1 signal. So this is corresponding to 40% more than the standard model rate. So scale it down by a little bit. So I mean, basically, we have these events which are pulling up. These are binned histograms, so we're not actually showing the exact mass values. So these they look further apart than they are. So it's like the normal gamma fit, we're just doing it with very few events. Okay.
If anything, the bottom left looks like it might be.
Yeah. So this is the overall. So it's a simultaneous fit to everything. So yes, if I fit this category by itself, we would see a deficit. But
It just looks like you got a bump in the wrong place.
yeah. So the bump here is really of course it's to guide your eye, but I mean it's the best fit result combining all channels in a simultaneous fit. That's not to say it's a good match for any given.
Only positive values are allowed?
We allow negative values. The fit prefers a positive one.
So wouldn't it make sense to, sort of open the floodgates so you have a lot of events and a lot of backgrounds? So if the background is smooth enough, you can always parameterize.
There's not much of a floodgate to open really. The leptonic category is almost as loose as you could possibly make it. The problem is not so much. I mean, certainly. I mean, okay, so you can open the floodgates and get lots of background in to understand the shape of the background. So that's what we do. But in order to get the signal, there's just not much more enhancement we can do for that. We could do a little bit in the hadronic category, but we decided that the important thing was to remove the long function part. So the limit winds up being, okay, so the observed limit is higher than the expected limit. The difference is, the thing is, this is an analysis where you actually expect the null hypothesis is there is a signal at mu of 1. So you expect, and this is actually, from now on, I'm semi-banning limit plots, but people understand that. But we didn't have the measurement bars. This is what we really should have, because what we're really doing is measuring the number with some uncertainty. We're not, the fact that the limit is high shouldn't be shocking, because in fact, if you see, say, the combined number, the observed black is quite close to what happens if you inject the signal. Need to speed up a bit. The interpretation of the diphoton coupling. So here's us scaling the standard model Yukawa, possibly to negative values. So we exclude everything where the curve goes below 1 here. So we're not, because the limit is quite high over here, we don't actually exclude particularly well on the high side, but you see we're almost at an exclusion at -1. The exclusion is actually -1.2. So we're, with this analysis, very close to excluding just the simple sign flip possibility. And this is the likelihood contour actually. So you see we don't like kappa of around 4 to 5. And the reason is that you see the spike here, that corresponds to complete destructive interference between W at top and the Higgs to gamma gamma, so that would switch Higgs to gamma gamma off. So this is saying that we have some evidence that we actually have diphotons events being produced here, at least we're 1 sigma inconsistent with no diphotons. So it's 1 sigma evidence for the process actually happening. Okay, so moving to BB bar, the bigger, the biggest single branching fraction, the mass resolution is much, much worse. Also, you can't, these events already have B jets in them, so you can't point at them and say, okay, the diphoton, these 2 photons must be for the Higgs. Here you can't make that, you have a bunch of combinations. And also the background, the main background is DT bar plus heavy flavor jets, DT bar plus BB bar. This is very tricky to model. We've just been able to get NLO differential distributions for that. We don't really have the full simulation at next leading order. So this is just hard. So our strategy, this is similar to CMS's, not everyone does this. You sort events by the number of jets and VTACs. So you say, okay, this event has 6 jets, 4 Bs, 5 jets, 3 Bs, whatever. And then in each channel, you train a neural network in our case, and then you classify the events. And you use the background rich channels to constrain the background. So you fit the full distribution of these discriminants, and you use the background rich regions to say, okay, well, this is how TT bar is going, or TT bar plus heavy flavor is evolving from one jet bit to the next. So we use the fit to simultaneously constrain all the background shape uncertainties as well as the signal yield. So for now, we only have lepton plus jets and bilepton. All hadronic hopefully will happen. As I say, that one's different. So the event selection, we're actually able to use single lepton triggers with full efficiency of 25 GeV. Not so much for run 2, but for run 1, yes. And they have fairly unified choices between lepton plus jets and bileptons, so they don't have any overlap. We make sure to fit beta is ease. And everything is uniformly using 70% working point, so you do in fact have light jet contamination all the way to the high jet bins. This is just showing the, so this is the signal to background S over root B for each category, going from 4 jets 2 Bs to 6 jets 4 Bs inclusive for the single lepton, so you're getting S over root B of somewhere around 0.7. In Dai Photon, this is before doing all the MVAs, of course. In Dai lepton, okay, it's worse, you just got much less signal, but it's quite nice. And this is the Higgs composition, so Higgs decay composition. So the red is Higgs to B bar. When you're in the most signal-rich regions, it's mostly that. But there is a component of WW in red, which is accounted for. That happens because you can have things like W to charm strange, and then the charm gets tagged as a jet. The backgrounds, so uncolored is TT bar plus light, dark blue is TT bar plus BB bar. In all cases, your main background is TT bar plus something, plus some kind of jet. It evolves from being mostly light down here to mostly heavy here, but again, this evolution you can constrain by looking at all these categories, you can constrain them. Interesting here in the 3B categories, we have a significant charm contribution. Okay, so top pair modeling, I'll vaguely, if you're interested in the details of this, this is the sort for experts on this channel, but what we found is that we're actually using a NLO generator using Poway, matched with Pythias 6. So you might say, well, this thing is not generating heavy flavor at high jet multiplicity, how can you do that? The interesting thing is when we studied this, because we actually got very, very good data, much better than the supposed high order, the leading order with many leg generators. What we found was the vast majority of what we were looking for was actually coming from the Barnum shower part of the jet generation, not the matrix element. And one moral of this, and ask me later why I put this in there, is if you just try and guess the regions where the matrix element is the important part versus where the parton shower is the important part given the matching cut, you are probably going to be very, very wrong. Which is part of why the analysis is not, I was not out a year ago. So anyway, so we find the best agreement with actually just an another generator for TT bar. We do apply some reweighting to match the data for the inclusive TT bar spectrum. We find that the generator is a little too hard. It's actually within systematics pretty much, but we just scale. And the data, our data do support the scaling when we do the fit. So pre-fit, so this is sorted into the N-jet categories from 4.2 to 6.4, single lepton and a dilepton. So you can see, okay, right now we're within the uncertainty bands for the ratios. There's some trends. The trends will go away once we do the fit. The neural network, so in the very signal poor regions, there's no real reason to train a specific discriminant in each one of them. So we just use the scalar sum of transverse momenta, either hadronic only or including the leptons. Then we do train in the low signal reach categories, neural networks, one for each one. There's also one that gets trained for light versus heavy. So even for these, you can still, because now you've got this discriminant, you can still partially unblind these categories and say, well, we will blind events where there's more than a couple of percent likelihood, a couple of percent contribution of Higgs decays. We'll just keep everything else. We'll look at everything else. And that again helps you validate that you're modeling your total top cross section. Okay, right, these are the slow slides. So maybe I'll just say there are some variables. They discriminate signal and background. So some of these things you might not necessarily guess. So their variables are essentially saying, for the Higgses, we expect two jets relatively close to each other, two B jets relatively close to each other. Also, this is actually a mass plot, a Dai E jet mass plot, which shows the kinds of not very great resolution. So the red line would be the signal. Not very great resolution on it, but you do see that actually the biggest difference is in the sort of 120 GeV bin. We also expect these events to be somewhat more central than generic TT bar, because you're really producing these right at the kinematic edge of what the LHC can do in PP collisions. So in fact, these things are not going at very high rapidity at all. So you can actually, this is one of the most strongly distinguishing variables in the separation. Now, if you look in, so this is the modeling of these variables in the low signal-like categories. For the dileptons, you really don't have very many events. Even, okay, lepton-plus jets, not so many. The red is what the expected contribution of TT bar Higgs be. So we do this bit of statistical magic profiling during the fits. That basically means that we input some things. We say the shape of the TT bar number of jet spectrum or number of B spectrum. That is, we give an uncertainty. We allow this. We have a nuisance parameter that allows you to morph between different distributions of this. And then we say, okay, fit. Go and tell us what the data favor. So the presumption is that the data will override our if the data don't have an opinion, then effectively this is just adding the uncertainty in this to the uncertainty on the output. If the data do prefer a particular thing, then the data will constrain that thing, and we can ask, do we understand why the data constrain it? And so there's a lot of back and forth that goes for this, but in fact nothing gets super over constrained. So we believe that everything we're doing makes sense. This actually gives us an in situ charm tagging measurement, effectively. So all the control and signal regions are simultaneously. You can do things like compare electron and muon and so on. And everything agrees. So the largest systematics in this case are coming. So I didn't mention systematics for gamma gamma because they're totally irrelevant. It's completely statistics-dominated analysis. Here, the largest effects come from TT-bar plus semi-favor overall normalization in the most sensitive pins. The reweighting of the momentum spectrum of the TT-bar and the B-tagging uncertainty. So you have 4 Bs, you've got the compounding your uncertainty every time you add one. So what does this fit do in background-rich regions? Well, so this shaded this hatched region is the uncertainties before the fit. After the fit, you basically can't see them. And in fact, what you expect the fit to do, assuming it's doing a reasonable job, is you expect it to collapse the systematics to roughly the statistical error in each bit. So that's precisely what happens. The hatching is about the size of the statistical uncertainties. And you see there may be some shape effect here due to we haven't applied a momentum reweighting that gets taken out. So in signal-rich regions, again, so here actually this gets constrained much better than that because now we're constraining the systematics from all of the regions where we have lots of statistics. So here, in fact, the systematics are smaller than the statistical errors. And what this does, it doesn't make the systematics go away. It's not telling us the systematics are 0. What it's telling us is that if you vary this one, you have to vary another one to compensate. So it's building the correlation matrix of what's allowed to be compatible with data. So the reason this is much smaller in this case is not because it's doing a super constraining job. It's because it's telling us that some variations are just not compatible with each other.
I'm sorry, I got slightly lost. So when you do the fit, you do the fit on what variable?
So this is the fit on the output of the neural network in this high B-jet multiplicity bit.
Right.
So the low, it'll probably take.
So before you show a plot of all the different beams, right? In all the different shed beams and beta
right.
beams, right?
So this chart is so here we're fitting some of
HT, okay,
HT
and the other ones in
HT,
got
and
it.
then we have NN.
Okay. And so the other question I had is how many nuisance parameters you have?
A lot. It's the sum of all these numbers. So we have 22 nuisance parameters for the jet FAG scale because the jet people are very enthusiastic.
Yeah.
For B-tagging, we have sum of 24.
Because that what I'm saying is that certainly help, right? Having a lot of nuisance parameters when you profile.
Yeah, but the thing is, what we find is the vast majority of them aren't constraints, so that means it's not really helping. But what we find is things like you can't vary the TT bar PT spectrum while I can't off the top of my head think of a very specific correlation, but like you can't vary the top PT spectrum and not change the B-tag efficiency, for example, right? So there are correlations that come as a function of PT, which is one of these systematics. So there are correlations that come in like that where the fit tells you you can't do these two things at the same time. Somewhere here I actually have, okay, so this is not showing correlations, but this is showing the post-fit uncertainty. So these black points with their error bars, if the error bar had the full width between here and here, it's kind of an ugly way of describing it, that if it had that full width, then that we wouldn't be constraining it at all. So this point actually tells us that we're constraining this about, I forget the exact number, 30-something% to 30-something% of the initial number, initial uncertainty, and we've moved it up a little bit. So this is TT bar plus BB bar normalization. So what this is saying is we're able to measure the rate of TT bar plus BB bar, which you expect to be able to do. It's you're seeing a lot of it. That's most of your background and one of your bits right here, the blue. And you're constraining it, and it's also slightly high compared to what you have put into the fit. Then say here light tag 2, the fit prefers the number to go down a little bit, but the error is not changed. So it's moving the central value slightly, but not in a way that's inconsistent with the error that you put in. So what it's saying is every single thing here is within 1 sigma of what we put in after the fit. The hatches are showing, so that this should be compared with this upper scale here. Those are showing you the effect of the 1 sigma variation on that parameter post-fit on the signal strength. So this is telling you that the TT bar plus BB bar normalization gives you about a 15% uncertainty on the fine line.
So, do any of your error bars actually grow post-fit? I'm looking at TT bar plus V cross-section.
Yeah.
Almost looks like it's ever so slightly bigger.
Just figure out
It's
which one
not
of
much,
these.
of course,
Oh, here, yeah. That's shifted slightly up. So the thing is, TT bar plus V, we have, that's a green here, actually. So it looks quite like, because it's TTZ, Z to BB, it looks quite like, but not exactly like signal. So there, this is saying that we actually really don't measure it, and we've relaxed the constraint entirely, and we still don't measure it. It doesn't change our fit very much. But yeah, the fit vaguely prefers a slightly non-zero shift now. Okay, you see, this is what I made the comment about the charm tagging. This one particular component of the charm tagging is actually pretty constrained, which we expect. Okay, so the results combined limit 4.1 times standard model, expected 2.6. If you injected the standard model signal, you get 3.4. So again, you expect that in the presence of the signal, you would see not the expected limit. The best fit rate is 1.7 plus or minus 1.4. Sorry, this is not the BB bar. The BB bar is, no, this is BB bar. What am I saying? Okay, yeah, so it's still in BB bar. So the best fit is 1.7 plus minus 1.4 for BB bar only. And one thing is, okay, so the green here is what we're complying statistical. The black is statistical plus systematic. So you might say in the combination, oh, well, you know, you're still systematically limited. But most of the systematics, because of this profiling procedure, things like the normalization of TT bar plus BB bar, we constrained it better with more data. So this is the largest single thing to worry about. So it's not purely, you know, 1 over root L, but it's pretty close on a bunch of the leading systematics. So we're not so bothered. It's just how exactly you choose to split them apart. And the signal, so this is a signal to background plot. So this is taking all the bins that are used in the fits, sorting them by the expected signal to background. So here, left side very unsignal-like, right side very signal-like bins. And you see, okay, so the limit is so this is the ratio with the background. The limit would be the yellow dotted part. So you see we're not, especially the last bit, not consistent with that really, but rather consistent with the best fit point. The best fit is the red, so we should be consistent with that. Okay, so now just looking a bit towards the future. So multi-lepton results. Actually, I have to combine. So this is not an approved Atlas result. We don't have one, but we derived these part of snowmass. And actually, we found, and the CMS sees this too, is that even at current luminosities, multi-leptons are competitive with BB. So even though the BB has been the standard channel for this since forever, well, one day we said, oh, let's try the multi-lepton, but actually, that's pretty well. So this basically, you know, we can say, okay, we have 1.4 here, maybe we get 1.4 from a completely different channel, completely different backgrounds, highly uncorrelated. So now we're talking about 1, which is the CMS result. So the most sensitive channels we have now, 2 leptons, same sign, 3 leptons. In the future, and I'll show you in a moment, we expect 4 leptons actually should hold Blitzo due to a very low fake lepton rate. So the main background in multi-leptons is top pairs plus fake leptons, and TT bar plus vector bosons, so TTW, TTZ. The snowmass simulations here, they're based on a parameterized detector simulation. I pronounce it Delphi's, but everyone seems to do it differently. So in particular, this gave us no opportunity at the time. We were dealing with centrally produced samples. We had no opportunity to tune isolation or anything. It's not even entirely clear that that would have made sense. But anyway, the fake rejection was what the fake rejection was. One thing we found, so maybe the key thing that we found was that we're getting most of the rejection against top plus fake in these analyses from the jet counting. So we're able to say, well, we expect many, we expect several more jets 2 or more jets than we would get from a generic TT bar event. So, you know, in all these cases, we're basically requiring dileptonic TT bar, which is only going to give you 2 jets, both these. So then you can say, well, I expect 2 more jets, or even more than that. And that really cleans up the TT bar. The pileup in HLLHC conditions confuses this jet counting. It requires you to either raise the jet thresholds to reject more of the pileup jets, or just take it. What we found is there really was no way to tune, within the parameters of the simulation, there was no way to tune the cuts so that we could recover the 3 lepton sensitivity in these conditions. So in fact, for the 3 inverse atom barns limit, 4 leptons took over as a more sensitive channel. 3 leptons is didn't do it anymore. In fact, here are the plots. So the yellow, okay, we're dealing with lots of statistical issues, of course, fluctuation in the backgrounds, but the yellow is, no, not the yellow, yeah, the yellow, sorry. The yellow, yeah, so unfortunately there's 2 different kinds of yellow. This yellow here, the one on top, is TT bar. So this bin, don't worry about it, that's supposed to be a TT bar control bin, so that's not wrong. The unshaded histograms are the signal. And so in fact, so here you see 4 leptons, this is times 5, and this is the number of events you expect. So you don't expect very many events, but very, very, very good signal to background here. 3 leptons, you can find bins that have a reasonable number of events, S over B, 1 to 2. So not very much yellow on the left. On the right, under these pileup conditions, completely washed out. And again, we found no way to recover being able to see these events underneath that. Now, it's entirely possible that we could actually, you know, we can be clever, but this is, I think, an issue that really needs to be considered for studies of this kind. So this is the reason in this case, 4 leptons still pretty much not affected, and we were able to get a pretty good number from those alone. So in the end, getting about a 9% uncertainty on the rate of 3 inverse atom bars. In fact, at this, somewhere between 300 and 3,000, you're running into the current theoretical uncertainties on the cross-section for production. So in fact, those have to be addressed on the scope of the technique to allow us to extract the power coupling at the precision we'll be able to get experimentally. Okay, so looking towards the immediate future, so at 13 TeV, the cross-section goes up a factor of about 4. So you see here's the cross-sections as a function of energy, TTH going up very rapidly compared to the other associated production modes. There's actually an Atlas upgrade that helps no new innermost pixel layer, it's so-called IPL, it's a B layer. So here's a preliminary look at how it improves your tagging, your mistag rate for fixed, well, for given feature efficiencies, and for not the super tight, not the super loose cuts, but for the tighter cuts, you're looking at almost a factor of 2 improvement in that. So that's actually something that for the analyses that need to categorize, that's very, very helpful. And extrapolating, you can see the sort of uncertainties we have now. I think the observation of the process at 5 sigma is very likely in the next few years, well, basically 1, 2. Though it will, to actually get over 5, you probably need both experiments. But each one is probably in the 3 to 4 range on its own. And you know, when we actually, so that's the first step, then we actually see something, then we can start asking questions about, is it high? Yeah, CMS. If CMS's central value holds up, then in run 2, we will have a many sigma signal for new physics. Right? If you're shrinking uncertainties from 2.8 plus or minus 1 to 2.8 plus or minus 0.2, you know, you're getting somewhere. Okay, so in summary, TTH is a key channel that constrains the top Yukawa coupling independent. Well, there can be effects coming from new physics, I should mark, but it's independent of new physics in gluon-gluon fusion. And it measures a key parameter in the standard model of Roentgen. There are multiple channels available to look for this. I've shown, you know, probably half of the total list that you could use. Discovery is going to be from a combination. It's not going to come from just one single channel. We're finishing up our run 1 analyses. We're looking forward to run 2, and I suppose I should add on to this as well. Pay very close attention to extrapolations to high luminosity, because just because you can extrapolate your lepton efficiencies does not mean you're extrapolating your jet counting correctly. So if you need the jet counting, pay attention. You can't just pile up really better. Okay, so any questions?
Phi sigma is what we must 300?
100. So again, if you combine everything, you combine Atlas and CMS, I think run 2 you can do it.
Second question, going back to slide T recession.
Not something I'm a super expert on.
So particle axis is coupled to TTH. Then even few points it's going to zero.
Yeah.
But you have a Higgs gamma which is from TT coupling. So how?
So I have to really talk with the authors, because this is something they say. Oh, and by the way, we'll show the top plots, but we won't really discuss. They don't put in any TTH constraints on these plots, really, so they're not discriminating based on actual TTH. Yeah, but these are all consistent with H to gamma gamma being 0. Being 1. So they're all consistent with the standard model. They're all consistent with the measurement that was available at the time. So actually, they're probably consistent with 1.6. Right,
Yeah,
which may be how you're getting it, because it may be.
Yeah, but the
we can have this.
projection is from TT bar to
Yeah.
fusion.
Yeah.
We need to
Again, I would have to actually talk with these folks. The point is essentially they're saying that you can modify the gluon-gluon within the constraints of what we know about the gluon-gluon fusion rate. And bear in mind, I mean, that's because you can play this game of increasing the production cross section and having it decay visibly, which will happen in some fraction of these. And so it's not the overall observed rate is not actually as strong a constraint on TTH as you'd like. Maybe that's something I didn't mention, but that is true. So there are games you can play, and it's not always obvious, but it is actually. I should ask them explicitly why you get these things that aren't near 0. And this is the rate using the modification to the observed rate, so it's square.
Any other questions or comments? No? So let's thank Peter again.